Probably this is Tilak. I have just one basic question. So
Yeah,
in the starting, in the groups, you have mentioned, you have written a truth table, right? Kind of truth table. Could you explain how it came? I couldn't understand. Thank you.
yeah. So here, so you can, this is say element one, and this is the second set of elements. I multiplied this element and this element to get this, the cross element. So,
Uh, okay.
so I define my operator with this uh, result. So I can just define rather a dot b is equal to some a or something. But this will lead to issue where we have just three elements. So if we have a dot b is equal to a, this will give us b is equal to the identity element. Basically, I'm canceling a. This is the only possible operator which I can define for three element group. So this table is constructed just by taking the row and column leader and multiplying and adding it and putting it inside the table here.
So you're saying if I do any operation with multiplication or with a dot, the resultant will
Yes.
be again in the same group, right? In the same
Yeah,
group of three
that is
elements.
the requirement of a group. So it has to be
Right.
closed.
Okay. Okay.
So
Yes.
closure.
Thank you.
So if I have such a set which satisfies these properties, then only they're called a group. Otherwise, they won't be a group.
Got it. Thank you.
So let's before proceeding, let's see some examples of fields. All the fields which we will discuss, we will be like talking about are all commutative fields, but there exist non-commutative fields also, which we will not go into too much extent now. So some examples. The rational numbers. So rationals are all numbers that can be written by in the form of a plus b, where a belongs to z. So these all form a commutative field with the operators plus and standard multiplication operators. The integers are not a field. This is a counter example. So they're not a field because they don't have the multiplicative inverse. So the most relevant to us field is the complex field. So the complex field consists of all complex numbers, which can be written as a plus ib, where I is defined as root of -1. So this forms a field under normal addition and multiplication. Or you can try verifying this later. Or you can just by verifying, well, what you need to do to check something if it's a field or group or not, just check whether it satisfies all the axioms. See all the border cases. See if there's any exceptions. And finally, uh, fields, all these fields, or this is not a field, but all this and this are infinite fields. They have infinite cardinality. But we can also have finite fields where the number of elements is finite and given by number d. One possible example is when you add and multiply modulo d. By modulo, I mean I divide by d and I take out the remainder. So for example, if I have 7, if I write 7 mod 3, 7 mod 3 is 3 into 2 plus 1. So this goes out, and this is my quotient, 2 is my quotient, 1 is my remainder. So 1 will be the element. So we can one can show that f p only for prime or powers of prime. You can show that they form a proper field. Not for say if you have d equal to r times s. This is not a field. This is not a field. A simple way of seeing this is R will not have an inverse. So this is not much of an importance, but just note that this is a finite field. It is not always a field. A finite field of dimension d is not always a field unless d is prime or a power of prime. So another useful quantity which we don't mostly need, but just for knowledge sake. So we have something called a field characteristic. So I have an operator plus, and I have the element say x belonging to this field, finite or infinite. So say x plus say I repeat this addition n number of times, n times, n is some integer. So this is something like n dot x. Remember, n need not be in the field. So this need not be a part of the field. So this nx, if it is added n times in the field itself, so this is not a proper notation, but just for our convenience, if this is equal to the identity element, addition identity element, say 0, here n becomes the characteristic of this field. Similarly, I can also define a characteristic for the multiplication operator, x times x times x, x. So this is basically x power n. If this is equal to a multiplicative identity 1, or whatever it is for that particular field, here n becomes the characteristic. So this leads to very interesting properties, but it is of no use for us right now. So this is something you can go check out later. So let's proceed to the most important part of today's tutorial. It is vector spaces. If anyone has any doubts, right now will be a good time to ask. Okay, I'll proceed since there's no questions. So a vector space is, in a way, a collection. A vector space is defined over some field, and it is a set of objects called vectors. So this is a vector space, and these V's are elements in this vector space V, and these are defined with a field F, a scalar field, which we call scalar because that's what they're called. And they have two operators, plus and multiplication operator, just like a field. So these are called vectors, and that's just a name again. And they satisfy two properties and some axioms which can be derived from those properties also. So the main properties from these operators are addition of two vectors. I call them V1 and V2 as two vectors. Usual notation for vectors, we just write them in bold. Since I'm not able to write a bold letter here, I'll just do this line on top. So V1 and V2. So these are vectors. So addition operator goes from vector space V to V, V cross V to V. Multiplication also goes from V cross V to V. So multiplication, apologies, I'm wrong. Multiplication goes from the field times V to V. For example, I say V1 plus V2 here belongs to the vector field V. Here, A times V1 belongs to V, where A is a scalar from the field. It's some number or some element in that field F, which we call scalars, just to differentiate between this and this. A is a scalar. So this is something like a closure requirement for vector spaces. So now, similar to fields, definitional fields, you have the associativity, commutativity, identity, inverse. So apart from those basic requirements, we have the scalar multiplication. So if A BV is AB times B, where A and B are scalars belonging to the field F. And you have the int scalar. So 1 times V is V, where 1 is the int element of the field. And you have the distribute. It is A times U plus V is AU plus BV. And another one is A times B. So this basically gives us the interplay between the scalars and vectors. Apart from this, we will have the associativity, commutativity, identity, and Filezilla axioms. So till now, I've given a very abstract idea of what a vector field is, so a vector space is. So let's see in more concrete terms. So a vector space can be written in terms of its basis vectors. So a basis vector is basically a set B, which can be a subset of the vector space, which has a property that all the elements Bi in Bi span the vector space. That is, for all V belonging to the vector space, I can write V equal to I can always find the linear combinations of Bi such that I have uh, V1 B1 plus V2 B2 Pn Bn. I'm assuming a finite dimensional vector space. So here, these are the coefficients of my basis vectors. So these basis vectors are still some random objects in this vector space. And these are the coefficients. And these coefficients belong to the scalar field F. So thus, if all elements in the vector space V can be written in terms of linear combinations of the basis of these vectors are called basis vectors. And there's a mapping between this vector element and the list of the scalars. So this is, in a way, a representation of my vector element in this vector space. So here, n is the dimensions of the vector space. So if I have infinite, or if n is say infinite, that is still a valid vector space, and I will have an infinite set of basis vectors. And one example for infinite basic vectors is basically functionals, wave function defined in a real space. They are infinite dimensional because the real line is infinite. So let's look at some examples. So first example will be the basic V equal to R square. That is the two-dimensional plane. You have X, Y coordinate, which you're used to. And here the basis elements are basically my line along x-axis and a line along y-axis. So I can represent my B1 itself as a sum of, say, B1, B1. So I'm writing, it's like I'm representing my basis vectors itself in terms of the same basis vectors. So this will give me B11, B12, this tuple as 1, 0. So this is a scalar representation of my basis B1. And I similarly can write B2 as 0, 1. So this is a standard basis. So thus I can write the V belonging to say R square. I can write it as a combination of VB1 plus V2 B2, and this can be likewise written as V1 comma V2, as this is 1 0 and this is 0, 1. I'm basically adding these two tuples as it is. I can write as v1, v2. So this is a simple R² vector space. So further on, all the vectors will represent their scalar elements, scalar representation, that is this representation, as column vectors. So this will be the notation we use from now on. So another example which is of relevance to us is the vector space, complex vector space of dimension 2. So here, all elements V belonging to V equal to can be written in the form C1, C2, where Ci belongs to the complex field. So this is basically a complex vector space of dimension 2. So and also so before we proceed to matrices, let's look at something called a dual of a vector. So a dual is basically can be considered something like a function of V, which goes from V to the scalar f. So, and this space of functions is called the dual space of the vector space V. So let's look at one example to get an idea of what I mean by a function. It's also a linear function, by the way. So if V is equal to the complex vector space which we defined earlier, the dual space will basically, and all of these elements can be written as C1, C2. The dual space, one possible dual space is I can take all the vectors, the duals of this form, such that when I apply, say this is f is equal to this. If I apply f on, say, v, on the element v, so I can define my application, the function as a matrix multiplication. So this will give me d1 c1 plus d2 c2. So this belongs to the field f because all these products are scalar. These all are scalars belonging to the field. Thus, the product of scalars also belongs to scalar, and that is the field f. So thus, this is a dual of the vector. This belongs to the dual space of the vector space. So you can see that one interesting thing over here is the function f, which is given by d1, d2. It is linear. As in, what I can do is say I have v1 is equal to some c11, c12, and v2 is some v21, sorry, c21, c22. If I apply the function on v1 plus v2, this is basically d1 times d2 times c11, c12 plus c21, c22. Effectively, I can just add these vectors and apply the dual, and I get c11 plus c21, c12 plus c22, and this will give me some scalar. So you can find it. So effectively, this is the same as applying function f on first v1 plus function of v2. So this property where I can apply the function first to the vectors and then add them rather than adding the vectors and applying function is, in a sense, the hallmark of linearity. And this is called a linear map. So formally, a linear map is basically a map going from one vector space to another vector space. It can also be a scalar. So this can also be a scalar. So the requirement of a linear map is basically f of v plus w is f of v plus f of w, where f is the map. And also f of a scalar times the vector is a scalar times the function of the vector. Basically, I can take the scalar outside. So this can directly be shown by this. So generally writing this, I can write as a b plus bw is a f of v plus b f of w. So this is a linear map. So a linear map can be completely specified by like finding its images or mapping on the basis vectors. So if I have f, which goes from say v to w, by knowing f of all the bases, I can this totally determines the linear map. So basically, if I have say x is belonging to the initial vector space v, xn, and the linear map takes x to y, say y1 till yn, then I can write yi is uh, some linear combination of the initial elements xi, xj over here. So effectively, each element here is a linear combination of the elements in uh, of the input x. So this can be represented as a simple equation where I write the elements A's as a matrix X, sorry, as a matrix A multiplied by a vector X. So here A is a linear operator in its matrix form. And if F was from V to V itself, then A will be a square matrix. So that is pretty much about linear operators. And there are some criteria when when linear operators are invertible, etc. Usually, if they are invertible, they are called isomorphic maps, and the space is called the space is an isomorphic space. So before we proceed to Hilbert spaces, let's look at eigenvalues of a linear operator. So say you have a linear operator f, which is represented by the matrix A, which acts on the vector v to v. So if v belongs to if that eigenvectors are defined such that uh, just a minute. Yeah. So eigenvectors are defined such that A v is lambda v, where lambda is belonging to the field f. V is other vectors, and A is the operator, the matrix representation of the operator. So eigenvalues are of interest for us because these are stationary with respect to the action of these linear maps. So this will be very useful when we wish to study quantum systems, where we want to where evolution of these stationary states are easy to follow and thus make a computation easier. So I'll walk you through a simple example of determining the eigenstates. So let's consider the matrix given by the following, which is basically the Hadamard gate. So this is a matrix on the vector space. So it's a C cross C, that is, it's a linear operator on the field C. H goes from, H goes from C square to C square, and it's given in this form. So we want to find the eigenstates of this. So we start off with writing H V is lambda V, and lambda is the eigenvalue here. And when we take this to the other side, we get H minus lambda identity operator is V. This is 0. For this to have non-trivial solutions, we need determinant of H minus lambda I as 0. Otherwise, it will only have trivial solutions of V equal to 0. So for this to be true, let's try the calculations. We get 1 minus 1 minus lambda 0 0. The determinant of this. We require this to be 0. So this gives us an equation in lambda, a quadratic equation in lambda, which will be of the form it should be of the simple form minus. So effectively, when you solve this equation, you get lambda equal to plus or minus 1. And this basically tells that the eigenvalues are limited to plus or minus 1. So now we can plug this back in our equation for the state. So here we add plus or minus 1, and we try to determine V from the given from the equations which we obtain. So the equations which we obtain, say for lambda equal to 1 case, let's try 2 cases separately. So we get 1 by root 2 times 1 minus 1 V1 V2 is V1 V2. So this gives us V1 plus V2 by root 2 equal to V1. Likewise, we also get V1 minus V2 by root 2 is V2. This gives us V1 is equal to V2 by root 2 minus 1. This gives us root 2 plus 1 if I take it out. So here, both the equations give the same expression. So effectively, we get vectors of the following form: V1 V1 times root 2 minus 1. So it gives us 1 degree of freedom to change V1. So this basically comes from scaling my eigen state. So say if this is my two-dimensional complex plane, and if this is the vector, what an operator A does is either to scale this and also rotate the vector. So it scales it and also rotates the vector. But for an eigenstate, it keeps the vector constant. It can only scale it. So this is like so everything in this direction will remain invariant, will be an eigenstate. So this gives that freedom. So if we require that the state be normalized, what I mean by normalized is V1 square plus V2 square is 1. For complex, we'll take mod square. So this is a requirement for what we will see later in lecture 1, where we want the quantum states to be normalized. That is, the probabilities should be summing to 1. If this was the case, you can solve for V1, and you can get a proper eigenstate, a finite eigenstate. So some more notation. I hope this was clear. So some more notation which we wish to introduce now. So vector V belonging to the vector space V. So this can also be written using something called a direct notation. Right? V as just this bracket V. So this denotes a vector. So this is same as vector V. And the dual can be written as this, where I just changed the side of the vector, of the brackets. So this also, our usual convention is vectors are column matrices, V1 till Vn. And these are row matrices. We are V1 till Vn. So, and a dual multiplied by a vector, we know that this gives a scalar in the field, right? So we write this as V times V. Let's take, say, W in the dual space times V. So this should be a scalar. So this is notationally reduced to this notation. I'm multiplying a dual vector with a vector, and this belongs to the scalar field F. This is same as, so here we have the freedom to choose how we want to take this product of vectors. So the standard inner product, standard dot product will be where we take W1, W2, Wn, multiply this with the vector Vn, by matrix multiplication. So this will just give us Wi, Vi, and this belongs to the field F. So this is a standard inner product, and this is called the inner product of W and V. So the inner product is in a way used to measure how similar to vectors in the vector field are, or how to estimate the angle between two vectors in a sense. In two-dimensional and three-dimensional real spaces, you can call them as the angle. But in high-dimensional, angle is not exactly intuitively correct, but you can use that for our purposes, that idea. So a norm of a vector is, say, a vector V. I have a vector V belong to vector space. The norm of the vector is defined as the square root of the inner product with itself, the vector inner product with itself. So this is like something like a length of the vector. So for our standard inner product, this will basically be Vi square if Vi belongs to the reals. And for complex, the duals, so say my vector is given by the vector V1 till Vn, where Vi belongs to some complex number. This thing's dual, or Hermitian conjugate, or as it's usually called, will be a row vector given by the complex conjugate of all its elements. So this is again by convention, and by wanting the fact that we want this inner product to be positive semi-definite. That is, we want this inner product to be, so if you try taking the inner product of this notation, this convention, you'll see that we will get Vi. So this is basically modulus Vi square. So this is a real quantity, and it's always positive. It's real positive. So this sum will also be real positive. So thus, this norm for the complex vector space is also well defined. It belongs to reals. So because of this requirement, we define the dual to be of this form. So this is the convention which we'll have to use for the rest of the time. So moving on, a final note on this. So the Hilbert spaces, which I've been hinting about all this time. So a Hilbert space is basically a vector space with a inner product, as we had seen earlier, which also defines, which in turn defines a norm of a vector. And also, it should be complete, the Hilbert space. So by what I mean by complete is all the sequences in this Hilbert in this vector space. Say I have a converging sequence in this vector space. These converging sequence should converge to a point, and this point should belong to the vector space itself. For example, to see a non-example, consider the vector space given by rationals, given by the operators now normal addition multiplication. So this is not a complete space. You can find sequences of the form A by B, which are all rationals, belong to the rationals. And this converges to, say, some irrational, say, for example, root 2. So you can always find such sequences, and these sequences are called Cauchy sequences. So Hilbert space is complete, and completeness requires that all such Cauchy sequences, which are converging sequences, belong to the same vector space. So this is basically a Hilbert space, and this completeness comes very much in handy when we want to write elements of this vector space in terms of bases and etc. like that. So there are some intricacies over there, which I'll not go into right now. So just few more things, few more ideas about operators. So we had seen linear operators, linear maps earlier, which was given by matrices A. So have AX equal to Y. A over here is a linear operator, is a linear matrix, and which we also call as a linear operator. So some operators, so this belongs to if X belongs to the complex space X and Y, this A can be over C cross C. Sorry, if it's belong to the n-dimensional complex space, I can say A is over C cross C, and the mapping is given by Cn to Cn. And this is a operator over this complex space of dimension n, and there are different types of operators. So two main types is Hermitian operators, where I require that A dagger is equal to A. So A dagger is defined as A conjugate transpose. So if I have, for example, A is equal to, say, A11, A21, A12, A22, A conjugate is basically A11 conjugate, A12 conjugate, A21 conjugate, A22 conjugate, and then A dagger will be the A conjugate matrix transposed. So that will be A11, A22, A21, A12. So this is a Hermitian conjugate of the matrix. And if the Hermitian conjugate of the matrix is equal to the matrix itself, this is basically a Hermitian matrix. Another type of matrix is the unitary matrix, U. So say I have a matrix U. This requires that my Hermitian conjugate is basically my inverse of my operator U. So say U belongs to some U acts on some complex space of vector complex vector space of dimension n. So we require that the Hermitian conjugate of a unitary operator is the inverse of the unitary operator itself. So this by definition, this defines a unitary operator. And this is very useful in quantum computing, as we'll see in quantum systems in general, as we'll see in lecture 1. So if anyone has any questions, right now will be a good time.
Yeah, so I have a question like what is the difference between vector space and fields, because the properties are like same for both.
So vector space is something like extension of fields. So it's just another mathematical abstraction of abstractive. It's a mathematical object which has multiple dimensions. Field is a single dimensional thing, like it's just scalars. So a vector does not add like scalars. It doesn't multiply as scalars. For example, if I have A, B belong to the field F, A dot say A and B belong to the field F. I have that A, B, the product of these two belongs to the F. So if I have, say, vectors, v1, comma, v2 belongs to the vector field V, this product is not defined. We can't multiply two vectors. It is not defined. So effectively, they're just different mathematical objects which have different properties and which allows us to represent systems. So this is one way by how we can differentiate fields and vectors. Is it clear?
Yes, thank you.
Okay, so if no one has any questions, we can proceed. So we're going to talk about error correction systems now. So so we had taken vectors in some vector space V, which we had written in terms of this. So similarly, we have this notation where, say, we have the binary field as 0, 1. The n-bit string can be given by the notation f2 to the power of n. This is just a small notational thing. So let's look at some classical error correction. Now, why do we need classical error correction? So these classical systems are usually prone to errors, and errors can be random errors, can be correlated errors, uncorrelated errors, etc. Yeah, you have your hand up.
Yeah, the F2N means the n-dimensional field, right?
Yes,
Okay.
n-dimensional vector space.
Yeah.
So
Yeah.
F2 is the field here, and F2N is the n-dimensional vector space.
Okay.
Just a minute. Just a minute. Some people are having an issue joining the meeting. I'll just invite them. Yeah. Let's proceed. The issue is clarified. So classical systems are prone to errors, and say if we have a bit string, message bit string m given by m1 till mk of length k, and this belongs to the this is a binary vector of length k. Sorry. So say some errors added to this, some error e is added. So this gives some erroneous message. So we need to do some correction to remove this error so we can get m. So this is the whole idea of error correction, and to identify the error e and to remove them such that we end up with the message vector m. So some very basic way to do this is the repetition code. So if I have a string 0, this will be encoded to 000. We have 1, will be encoded to 111, and thus this adds 2 bits of redundancies. This is a mapping from f to 1 to f to 3, and this adds some redundancies. And now this allows us to decode this with something called the majority logic. So in my string, say if m is equal to 0, my encoded string will be some function of my m. It will be 000. And now in my for decoding, I can find the majority bits. So here majority, if I have no errors, so here majority bit is basically 0. There are 3 zeros and 0 ones. So this will be decoded to 0. But say if I have an error, first I started message say 0. This is encoded to string 000, and some error is added. Say error is some 010. This gives me the erroneous string of 010. That is 000 plus 010. So this gives me 0, 1, 0, and this needs to be decoded now. So we find the majority number of bits over here. So 0 has a majority. So this will be decoded to 0. And so this will be correctly decoded despite having an error E. So here, as you can see, if the error say had was of the form 0, 1, 1, there were 2 ones and 1 zeros. This will be decoded rather to 1 because the obtained string will be 0, 1, 1 and have majority of 1. So this is a erroneous decoding. So here M is called the message string. C is the code string. And E is the error string. And this is of length K. This we usually denote by length D. And since over here, the maximum weight of error, so the weight of a string, we define the weight or the Hamming weight of, say, the string E, is the number of ones in the string E. So if E was, say, 0, 1, 0, this Hamming weight is basically 1. If it was 0, 1, 1, the weight will be 2. So the maximum so the number of the Hamming weight between two strings, say here the code space is given by the vector 0, 0, 0 and 1, 1, 1, and this is basically the code word. So if I have 0 message and have 1 message, this is encoded as 0, 0, 0 and 1, 1, 1 for the repetition code. And the distance of the code is basically the distance, literal distance, the number of bit flips between these two strings. So distance of, say, 0, 0, 0 and 1, 1, 1 will be basically 3 because I need 3 bit flips to go from 0, 0, 0 to 1, 1, 1. And so this can be given by the minimum of weight, say C1, C2, belonging to the code C. Minimum weight of C1 minus C2. I'm literally counting the number of the bit flips I need from going from C1 to C2. So this is defined as the distance. So thus code C can be given by 3 parameters. One, the length of the code word, the length of the message vectors, K, and the distance of the code word, which determines its performance. So let's look at another example of this. So this is an example of something called a linear code. To make this much more clear, let's look at the Hamming code. So consider this matrix, consider the message vector given by some, say, a row M1, M2, M3, M4, and consider the matrix G given by 1, 1, 1, yeah. So if you see this has a length of 4. So K is equal to 4. So now I claim that the code word can be given by the message vector times this matrix. So this is the message vector and I have the matrix of dimension 4 times 7. So what will this matrix product give me is basically a 7-bit string. So this 7-bit string is basically my code word. And since these are represented by linear operations, multiplication of matrices, which is a linear operation, these are basically called linear codes. And for linear codes, if I have say C1 and C2 belonging to the code space C, C1 plus C2 will also belong to the code space C. By code space C, I mean all possible code words in this code space. That is, if I take all possible message vectors and multiply it with the generator matrix, I will get a space of vectors. I'll get a vector space, subspace, and that will be that I can call as a code space, which has this closure property. So in effect, what I'm doing is, if I write the generator matrix as say a vector G1, G2, G3, and G4, each of this row is G1, G2, G3, G4. Effectively, what I'm doing is I'm writing C as a summation of mi Gi. I'm writing my code vector as a linear sum of my generator basis vectors. So effectively, the number of basis vectors GIs, the cardinality of GIs is basically my number of code words I can code word bits I can represent, number of message bits which I can represent, and the length of GI will basically give my length of my code word because of this because it belongs to the same vector larger vector space. So this smaller space C belongs to the larger vector space V, and they have this closure property that if I have C1 and C2, the sum of C1 and C2 also belongs to C. So since we are considering a subspace C belongs to the just a minute, I'll admit the people. Yeah. Since the code space is a subspace of the larger vector space, effectively that exists this other dual space of this code space. Dual as in this space is represented as can be represented as a linear combination of these basis vectors. So these will also have some basis vectors, say hi, which are basically orthogonal to my GIs. They are orthogonal. So since they're orthogonal, if I have the inner product of say the code vector with a vector of this dual space, this dual space, this will basically be a 0. So this leads to for all hi belongs to V minus C. So this leads to the following condition that I can write all these vectors as a matrix form. I can write C times h1 till h whatever the dimensions is. So usually n minus k is the dimension of the dual space. Since this is k, this is n, the dual space will have n minus k dimension. So this I can write it as the following condition. I have the code vector times this so basically I'm taking the code vector and writing it as a vector with scalars. And I can write them as a product with this matrix H, which lists out all the these dual vectors Hi as their rows. And this should be 0 because for every Hi, the code vector is perpendicular or is orthogonal to it. The inner product between those two are 0 because it belongs to a dual space. It does not belong to the same space. Effectively, Hi union Gi spans the vector space V, and this spans the vector space C. This spans the dual space CPUB. So what this tells us is, using H, we can determine our errors. So say I have the message M, which is encoded using the generator matrix G as vector C. So if I want to find the errors, I can just multiply this by the matrix H. And if this gives me 0, there are no errors. If this gives me something non-zero, that means there are some errors. So say the erroneous vector is C plus some error. This error does not belong to my code space. I'm assuming that it does not belong to the code space. So here what happens is, if I have CPUB, if I multiply this with the elements of my, if I take the inner product with the basis vectors of my dual space, that is H. So this will basically give me H C dagger, sorry, C transpose plus H E transpose. So this goes to 0 by definition because my code space is perpendicular to the dual space. And this is now non-zero because E transpose does not belong to my code space. So hence I can determine my error. Once I have this, I can just multiply this by H inverse and I get E transpose. So once I determine my error, I can I can take the erroneous code word with my error vector is basically my code vector. Because we have E plus E, this is basically 0 because I'm taking mod 2. So thus, just by using some basic linear algebra, I can determine my code word. I can determine my error first and determine the code word. So this holds only when the error vector does not belong to the code space. So this is the basic idea of error correcting when there are errors. First, we detect the error using my parity check matrix, that is H matrix, and then I determine my error string, and then I use it to remove the error from my erroneous code word. So any questions?
Yeah, so is it possible that the inverse of H always exists? So what if it is a rectangular matrix? How can we determine the error then?
So there are pseudo inverses for the H matrix, and since it's a binary field, we can always determine. So it is there is a way to do that. This is complicated, but yeah, we can do it. So it's not a one-on-one mapping. because error, I can always have like say, if this is the code word, I add an error E. So if this error itself is of the form say E prime plus some code word, where like C1 belongs to my code word space. Effectively, when I correct it, C plus E prime plus C1. So this basically will be corrected to C plus C1. So this holds only when the error vector is of lower weight. And so this is not a one-on-one mapping always. So there are cases where it's not possible. Yeah. So that it'll be miscorrection. Is it clear? So we usually take the pseudo inverse of sorts, and then we determine the error. So the normal inverse usually doesn't exist. The H matrix is usually rectangular, so it does it. Any questions?
Yeah, I have a question.
Yeah, tell me.
So you introduced the repetition code, so in which
Yes.
you like encoded 0 as 000, but then
Yes.
to motivate the linear codes, you have written a form of G. So that is a very different one, like a bit more complicated than what we started off with. So how do we decide what kind of coding we are going to do? Like what basis you chose a particular form of G?
So one thing, the rows of G, that is the basis vectors of this code space, they need to span the space, and we usually choose them to be as far as possible from each other. Far, what I mean by far is the having weight, having distance from one to one to another is as maximum as possible. So we try to maximize the distance of the code.
Okay.
So if
Okay,
I
so
have say C1, C2, let's take the basis of the codes, say G1 and G2, which are rows of the generator matrix G. And G1 and G2 belong to the code space C. So I try to determine the weight of G1 minus G2, and I try to maximize this for all possible combinations of Gs. So we can take different choices of Gs for different purposes which we might have. So sometimes the errors might be in localized in one particular place, and we can choose such basis. So it's up to us. So the only requirement is they are linearly independent.
okay, so based on various requirements, we can fix our G.
Yes.
Thank you.
Okay. If no other questions, we can proceed to the next part of the talk. I'll maybe share some resources for my part in the Slack channel by mail. Uh, Okay. So I invite Mr. Vaki to come and press the next part of the talk.
Yes, 1 second. Can you see my screen?
Yes, we can see.
Yeah. 1 second. Yeah, you can see now.
Yes.
So, yeah. So, good evening, everyone. So, the next part will be on the tutorial on classical computer networks. So, this will be a precursor for the talk by Dr. Peter Roth. We'll be talking on quantum networking. So, I'll be taking just the very overall picture of classical networks. So, I won't go too much into depth into the networking theory. So yeah, so we'll start on that. So I wanted to be a bit interactive, so I've used this Mendy.com to make it more interactive. So let's begin with the survey. So we just want to check how good you are at computer networks. So if you can just go there and then yeah, give your rating. I hope it works. One second, let me check.
Can you maybe share the link in the chat?
Yeah. One second, let me check. Now we should be able to. Okay, this is. Yeah, so I think around 33% have voted, and I think around 3.2 is the average, around 3. Yeah, so I'm guessing it's, yeah, we're not too aware of it. So yeah, I've made it only very basic, so I don't think it will be too complicated for you guys. So let's start off with the very basic computer. What is a computer network? So computer network is basically a set of computers sharing resources located on a owned or provided by network nodes. So basically, you have a bunch of devices like a laptop and mobile phones and iPads and all those things. So you just connect them using different medium like Ethernet or Wi-Fi, and then you get a network. So they use communication protocols like Wi-Fi or Zigbee or Bluetooth. If you can connect two devices, then it's basically a network. So it's a definition from Wikipedia. So we'll just start with what are the different types of networks. So the different types of network, you have the PAN, which is the personal area network. It is basically a USB, US Bluetooth. So it's just around the person. So then you have the a LAN, which is the local area network, which is limited to a geographical area, which is probably around your home or your office. Is a residence or a building. Then you have the MAN, where you have the metropolitan area network. You have several buildings in the same city or town connecting together into a single network. Then you have the wide area network, where you have a broader geographical area. So across towns and countries, you have multiple LANs. So it's basically the internet is example of a wide area network. Yeah. So if you have any questions, you can interrupt me. So I'll go to the next question. So, oh, already asked, answered. So, yeah, you can, if you haven't answered, you can answer it now. So, what are different types of devices that comes into your mind when you think of networks? Yeah. So you can answer. So, yeah. So far, I think you have very good understanding of the devices in a network. So routers, servers, switches. Yeah, most of these are there in the networks that you see. Yeah. Yeah, I think a lot of people are entering the network speed computing. Yeah. So I'll just go through some of these devices that you guys said. So one is a repeater, which is it regenerates a signal. So in the physical layer, the electrical signals that come up, it can attenuate. So it means that the signal power gets reduced. So the repeater repeats, regenerates a signal. And then there's a hub, which is a multi-port repeater. So it uses multiple ports to connect multiple devices, and then it regenerates multiple signals. Then the bridge is there, which is an intelligent repeater, which can direct the signals to a particular destination. So basically, in this, the bridge is directing the signals from this network to this network. And then we have the switches, which connects the devices in a particular network. So the switches connect in one single network. The switches connect multiple devices. So it uses a device MAC address to connect and to send the data between the devices. And then we have the router, which connects multiple networks together. So that uses a device IP address to connect between multiple networks. So the switch only connects devices in a particular smaller network, but the router connects multiple networks entirely. So it's something like the router in your home can connect your home to other networks, probably your neighbor's home, so like that. So that's what the router does. Switch, it only connects within your own home, like that. So the nodes are the laptops and the mobile phones that you use normally. Yeah. So then there are multiple network topologies. So you have the point-to-point, which is basically you just connect two devices together. It's a single dedicated line. Yeah. And if you connect multiple more devices, in a cascaded manner, you'll get the line that is for multiple nodes. Then you have the bus topology. So this is what you normally see in the offices. So you have multiple devices, multiple laptops or computers connecting to a particular single bus or channel, which is a single cable that is running across. And whatever data you send, this goes through the cable and then goes to the other laptops. Then you have the ring, where the ring, everything is connected in a ring fashion. So if you send a message from one device to another device, it goes through all the devices and then reaches there. So it is also fault tolerant, as in if you remove one link, then the device can send the same message in the reverse direction. So it is a bit more fault tolerant. So there's something called token ring. So they use this kind of topology. And then there's a star topology. So here, this is what you normally see in our homes. So we have a central router, which uses the Wi-Fi. And then all your devices, your laptop, your mobile phones, your tablets, they get connected to the router, and then you can send data. So all the data goes to the single gateway or router, and then that sends the data to the others. Similarly, we have the tree, which connects multiple other networks together into a single bus topology. Then the mesh topology is there, which connects multiple devices together. It need not be completely or fully connected, as in it need not connect all devices together. If it connects all devices together, it is called a fully connected or a complete network. So the mesh network, it just connects at least a few together. Then the hybrid network is there. So it basically a combination of multiple other topologies, but it should not be any other topology. It should be a combination of multiple. Yeah. So if you have any questions, you can interrupt me. So yeah, it's basically the point to point, which is the child's tin can. It's basically an example. Yeah. Anyone has a question?
Yeah, I have a question. You said that the ring
Yeah.
topology that is more fault tolerant. So could you just like comment something on fault tolerant and how that is more appropriate for that topology ring?
Yeah, it's not entirely fault tolerant, but it is somewhat more helpful than other topologies. So, example in the bus topology, if this connection fails, then this device cannot communicate with this device anymore. But in the ring topology, assume that this device can communicate with this device. So the message goes, it can go either this way or it can go this way. So in two ways it can go. So if the link fails here, it can still continue to send messages in this fashion, in the reverse direction. So to an extent, it is fault tolerant, but not fully. Yeah.
Okay, thanks.
So yeah, so we'll go to the. I mean, we'll just explain. So the point to point, it's basically the child's tin can, where you talk to each other on a tin can with separated by a string, and that's a basic example. So the linear, and then you connect multiple devices together. It is cascaded point to point, which is a linear topology. And then you have the ring topology. So you connect them in a ring fashion. So it's, yeah, as you said, that it's fault tolerant. I mean, a little more fault tolerant, and it token ring topology, token ring, yeah, that uses ring topology. And then we have the bus, which it goes to the backbone bus of the network. Ethernet uses this. Star network, where all the nodes have to go through the central node to communicate with each other. The home networks is an example. And then we have the mesh network, where multiple devices are connected together. So in a mesh fashion. So the Zigbee, which you may know, it uses the mesh network. It's an IoT device protocol. And then you have the fully connected network topology, and in this, all the nodes are connected with each other. Then the hybrid, it connects multiple topologies together. Yeah, so now we'll go to some basic computer network theory. So first is what is an IP address? So an IP address is basically a unique number given to a device within a network for identification purposes. So example 13, 22, 18, 9 is an example of an IP address. So there are essentially two addresses that a device uses in a network. One is the IP address and the other is a MAC address. So the IP address is mainly used for the first point of network connectivity, and then within the network, the IP address is converted to a MAC address to communicate the data. So this is basically the IP address. And then we have something called service. The service is an application. It's example, you have a website or you have a game server and you host your game on a laptop or a server, and then that's running on a device. So and these applications that you're running, it may be accessed using the device's ports. So there is something called the ports, which are there in the laptops or the devices, and that port is connected to that particular server, particular application, particular service. So for example, so there are these web servers. So let's say google.com or IIEEE-IISc website. So they'll be hosting a web server. So that will be hosting a website, and that web server is a service, and that will be connected by a port which has a particular port number. Similarly, file server, which is hosting a file, and the game server, which is hosting a game. So like that. So like Facebook.com, they will be having multiple data centers and multiple servers hosting the websites. So the services are the websites that are hosted on. So for the services, so you need to connect to a particular service. Let's say there's a device which has multiple services hosted on it. Like let's say there's a website hosted on it, there's a game server hosted on it, there's a file server hosted on it, mail server hosted on it. But you don't want to access everything. You just want to access just the website or just the game. So you want to access only that particular service. So for that, you have a particular number associated with that service that you want to access. So first, what you need to do is you need to know what the number of the device is, which is basically the IP address. Then you want to know what is the number of the service, which is a port number. So that's how we connect to a particular service. Let's say google.com. What I normally do is you just go to your browser and then you just write google.com. So what actually happens is it translates to a particular IP address along with the port. So the port will be normally 80 or 443. So that's how it actually connects to that particular website. So yeah, basically a port is a communication endpoint that identifies a service. So port numbers, they range from 0 to 65353, and yeah, so there are multiple port numbers. So there are some port numbers that are already assigned that these are the port numbers that should be used for this. There are some that are not assigned, which we can use for custom services. And yeah, so for example, the port number with port number 80, it's used for hosting web services. It's HTTP, which is not a very secure web service port. So yeah, so assume that there's a website with port 80. So let's say google.com. So google.com's one IP address is this one, 142.250.71.46. So how you access this particular website is you go to this address and then you press 80. So then it allows you to go access google.com website. So that's how you actually access the website. And then yeah, some port numbers are reserved like this. Like 80 is only for HTTP, which is for web service. For 43, then FTP it is 22, like that. Sorry, 21. Yeah. Yeah. So the incoming port numbers generally use the smaller numbers. The outgoing port numbers, they use the larger numbers. So when we are connecting to, let's say, google.com server, google.com will have either 80 or 443 as their incoming port numbers. But from our own device, we will also be using a port number which is called the outgoing port number. That is 65. I mean, that's probably a very large port number, and that is what google.com's server will be using to connect to our device, to communicate with our device. Yeah. So any questions? Yeah. Okay. So so the socket is basically a combination of these two things, IP and port. So it uniquely identifies a single network process with the entire internet. So let's say there's a device with which has an IP address 192.168.1.0, and it uses it has a website hosted on it. So it uses the port 80. So yeah, so this is basically a socket. So you use this to access that particular service, which is the website hosted on this device. Yeah. So then there's something called the private IP, and then there's something called the public IP. So private IP can only be accessed from within the network. So you can't access this from outside this particular network. So there are these ranges that are assigned to only private networks, which is 10 dot private IPs, which is 10.0.0.0 to 10.255.255.255. and 172.16 range and 192.168 range. So these are for private IPs. And then there are public IPs which can be accessed from anywhere in the world. That number is limited because IPv4 because larger number of servers have come up, and the number is limited. So so the range is basically almost everything except these three ranges. So for example, if you ping google.com, it gives this one of the IPs will be this particular IP. Yeah. So public IP is used when you need a device which is available publicly, as in you want it to be accessible from anywhere in the world. So normally web servers, file servers, which need to be accessed from outside, will be having a public IP. So you need to buy a public IP. So home networks, if you're in a home network, if you use your computer, then you'll be your router will have a public IP, but your own laptop will have only a private IP. So if somebody is connecting with you, what they will see is your public IP, which is your router's IP, but not your private IP. So all the devices that are connected to that router, your laptop, your mobile phone, everything will be having the same public IP, but they'll be having different private IPs, because in the same network, you'll be having different private IPs. Yeah, so it's like that. So if you're working in a company, you may see that you need to use VPN to access, which is basically virtual private network. You need to access your corporate network only to access certain websites. That is because you don't want it to be accessible to the public. So the public cannot access it if you're not in that network. Yeah, so those will be having only private IPs, not public IPs. So there's something called network address translation, which helps people. If you want to connect to your, let's say, your neighbor's device, you can't directly communicate with their private IPs. Let's say their private IP is 10.0.0.1. So you cannot directly communicate with 10.0.0.1, because if you try, let's say, pinging, which is basically let's say trying to communicate if the host is there. If you try pinging 10.0.0.1, then your device checks for 10.0.0.1 within your own network. It cannot find it because your network also will be having some other 10.0.0.1 devices. Yeah, so basically probably when you're pinging it, you probably find your mobile phone to be the one that you're pinging actually. So how do you communicate with your neighbor's device? So what you do is, so when you're communicating, what the network actually does is it goes to your router's public IP, and the router does something called network address translation. So the data that you send, it goes to the router, which is a public IP that is using, which can be accessed from anywhere. And then the router changes that address to the private IP which you are trying to access, and then it communicates. So it uses some algorithm, but that's how you are able to communicate with your neighbor's device. Yeah, so basically the router acts as a gateway between your device and your the neighbor's device. So this is basically network address translation. So let's say you are this host and you want to connect to connect to the server, and the server wants to talk back to you. So for you it is easy. For you just have to send you just have to directly communicate with the server. So the server's public IP address is known to you. So you put that address, then it goes to the router. The router changes the packet such that it is its source IP address. Then it sends the data to the server. But when the server is trying to communicate with you, what it does is it doesn't give the private IP, but it gives the public IP. So the server, it uses its source IP address and its destination IP address. The destination IP address is not your private IP, but it's your router's public IP, which is 150.150.0.1. So the data gets sent here. Then the router knows which device to send to. Then it changes the IP address to the destination IP address. So based upon that, it translates the address to private IP address. Yeah. So it's something interesting that it does. So this is basically used for conservation of the public IP addresses, which is the IPv4 addresses. So you may be knowing that the IPv4 addresses are very scarce, and we are going through IPv6 addresses. So that's why this network address translation is very useful to preserve IPv4 addresses. So yeah, basically the public IP addresses are actually it's over, I think. So the IPv4 addresses, it initially had only 4.3 billion addresses available. So it anticipated that it's getting over very soon. So that's why the reason we started to think about IPv6, which can connect more devices, especially with the IoT devices and all coming, it will be more useful. So yeah, so this is basically from Wikipedia, and the top level exhaustion, it started in 2011, and in Asia Pacific it got over in 2011. In the Latin American Caribbean it got over in 2014. North America it got over in 2015. Africa it got over in 2017. 2019 Europe, Middle East and Central Asia it got over. Yeah. So yeah, the ISPs may still have some unassigned IP addresses, and so yeah, and could recycle. Yeah, so the IP addresses that are no longer being used can be recycled. So if you want to get some public IP addresses, you can go to Amazon AWS or DigitalOcean. There are two websites who provide servers for you. So you can go there and then buy a server. So it's mainly around 500 rupees you have to pay for every month. I mean, if you're based upon your usage. So you can use it for creating a website and all those things. So yeah, that's. So the next thing is a CID annotation. So it's called a classless interdomain routing. It's basically used for finding how many devices are there in a particular network. So it enables to see number of IP addresses contained within each slash notation. So it denotes all the hosts in the same network. So let's say the subnet mask, the subnet mask represents the number of hosts in the network, and the initial first digits of the IP tells this is the particular network that we want to access. So let's say 192.168.0.0/24. It means that all the hosts starting from 192.168.0.0 to 192.168.0.255. So this is the full range. I mean, it's easier to write like this than to write like this. So it basically shows that this is the particular IP address. It starts with this particular IP address 192.168, and then it ends with any IP address within this range. So that's what it shows. So the technical details is basically you convert it into a binary, and then you, I think, XOR it or AND it with the with ones only in that particular area, and then in that particular area, how many ever combinations you can have, that many number of hosts will be there. So yeah, so there are multiple classes of networks. So there's something called the class A network, class B network, class C network, class D network. So class A is a very large network, and class B is a small network, class C is a small network, like that. So in companies, they'll be having large networks, small networks like that. So /8, it'll be used for a very large range. So basically this 3 octets will be used. /16 will be using only these 2 octets, and /24 will be using only this last octet. So only this last octet is being changed in /24. So in home networks and small office networks, we'll be using /24 to address the full set of hosts. Yeah, any questions? Yeah. So there are two models that we generally use for computer networks. So it's there's one thing called the ISO-OSI model, and then was something called the TCP/IP model. So it's basically to help in segregation of the data that is coming to your network. So the TCP/IP model is basically a truncated version of the ISO-OSI model. The ISO-OSI model has 7 layers. TCP/IP has only 4 layers. So it's basically TCP/IP will be combining these 3 layers together as the application, and the link layer and the physical layer as network access layer in the TCP/IP model. So yeah, so this is basically used for segregating the tasks assigned to a particular tasks assigned to the data that is coming to a particular device or a particular router. So we'll go through each of these layers quickly. So first one is the application layer. So the application layer is basically your application itself. So let's say your website or your mail server or your Skype or any application that you're using. So that application will be sending data. Yeah, let's say when you're browsing to google.com, the google.com will give you the web page. So that is an application, like sending an email, sending a file. So it's the application, it's data that it's sending. Yeah, let's say the web page of a particular website. So that's basically the application layer. So the application layer gives that data to the presentation layer. So the presentation layer will make sure that the remote host is able to read the data that you're sending. So it converts the data to a particular readable format. So let's say the application gives a EBCDIC code, but the remote host wants it in ASCII code. So it get converted in ASCII code, or make sure it is in ASCII code, like that. So that translation it does, and then compression it can do, and encryption also it will be doing. So compression is basically basically compressing the data so that it doesn't have to send more data. So, and then encryption is basically you're preventing attackers from eavesdroppers from getting the data using cryptographic methods. And then the next layer is called the session layer. So the presentation layer gives this data to the session layer. Session layer is basically to establish and manage sessions. So it checks if the session is on currently or if it is off. So if data is being sent from the application layer to the presentation layer, and the presentation layer is given to the session layer, if a session layer says that the session is already closed, then it no longer sends the data. So it's not required to send the data because the session is already closed. So some examples are the SQL database server session. So this database server called the SQL database. So they're just holding some data. So you're accessing the data, and then you first initiate a session, and then you start sending data. So if the session is closed, you no longer want to send the data. Then there's something called a remote procedure code also. So you remotely send a procedure to ask a remote host to perform a procedure. So in this, the sessions are handled. And then there's something called the transport layer. The transport layer is used for end-to-end connections. So it used for reliable data transferring. So when you send the data from your device to the other device, you need to make sure that the data is received by the receiver. So you can either use TCP or UDP. So there are two protocols which are used in the transport layer. So TCP is reliable. So it mainly, basically the data that is coming, it has a connection between the data, and then it checks if there's an acknowledgement received from the receiver. If there is no acknowledgement, the data is again sent to the receiver so that it is received properly. And in UDP, it doesn't happen. It just sends the sender just sends the data to the receiver. So that's what happens in TCP and UDP. So that's what is there in the TCP transport layer. So then there are there's something called the flow control. The flow control is basically to make sure that the sender is not sending more data than the receiver is able to receive. So if the receiver is seeing that it is sending more data, then it's not able to cope up with the data that is sent. So the sender reduces the number of data that is sent. And then for this flow control, the TCP uses something called the sliding window protocol that I'll cover in some next slides. So the congestion control is also there. So congestion control is basically for the network. The network has a particular capacity on how much data it can accommodate. So if the device sees that it cannot send more data, then it reduces the amount of data that is sent, so the network is able to handle it. So that all this happens in the transport layer. Then the network layer, it uses the IP addresses to send data. So it is basically inter-network connections. So from one device in a network to another device in a different network. So those kind of connections, for that you use IP addresses. So that happens in the network layer. So it is used for identifying and addressing devices in a particular network, and IP is used for it, and it also used for routing data packets. So interconnecting two networks, you'll be using a router. So the router is the one that checks the data and then sends the data to whichever device is required to receive the data. So for that, routing is required. So that routing happens in the network layer. Also, through multiple routers, the data has to go. So that routing algorithms also take place in the network layer. So it also works with the data link layer to convert IP addresses to MAC address so that the data is finally sent to the right MAC address. Then the next layer is the data link layer. So in the data link layer, the device to device data transfer happens. So in the particular network itself, the device to device data transfer. So it mainly uses the MAC address to find this is the device, and then it sends the data to that device. Then in this layer itself, there are two main properties. I mean, two functions of this layer. One is the media access control, which is basically to check if the medium, which is the Ethernet cable or Wi-Fi, is available for sending data. So for Ethernet, they use something called the CSMA CD. It is called collision detection and carrier sense multiplexes. So it checks the medium if it is available and then sends the data. And then logical link control also is there, which is basically the flow control I discussed earlier, which is basically if the receiver is able to receive the data or not. And then automatic repeat request, it basically checks if data is received, and then it again sends the data if it is not received. So also multiplexing for multiple protocols. So there are multiple protocols in the same network, so combining all these protocols together to send the data, that also exists in this layer. So the final one is the physical layer. The physical layer is basically the physical structure of the network. So it's basically the electric pulses, the mechanical pulses, the optical pulses. So basically these things. So it's useful when you have some problem in the network, and then what you do is you check the network. The network, is the cable correctly put into the device? Is the network interface card working properly? Things like that. So it uses bit by bit and symbol by symbol data transfer, and it uses line coding. It's if you're from an ECE background, you'll have this background. So basically, you convert the digital data that you receive, like ones and zeros, you convert it into different ports, which is basically mechanical and electrical pulses. So that gets transferred through the network, and then it gets decoded back. And then circuit switching and multiplexing of sharing of devices. This also occurs in this layer. So some of the examples of this, what devices that are in this layer, it's the RJ45, the Ethernet cable. So these are two examples of the devices in this layer. Yeah, so any questions? Yeah, I hope I'm not going too fast. So I'll just go through a video. So this video basically combines all what we just heard, and it shows a very basic how the data transfer happens from your device to the other device through all these layers. So yeah.
Now that you know the basics of how every layer of our network model works, let's go through an exercise to look at how everything works at every step of the way. Spoiler alert, things are about to get a little geeky in a good way. Imagine 3 networks. Network A will contain address space 10.1.1.0/24. Network B will contain address space 192.168.1.0/24. And network C will be 172.16.1.0/24. Router A sits between network A and network B with an interface configured with an IP of 10.1.1.1 on network A and an interface at 192.168.1.254 on network B. There's a second router, router B, which connects networks B and C. It has an interface on network B with an IP address of 192.168.1.1 and an interface on network C with an IP address of 172.16.1.1. Now, let's put a computer on one of the networks. Imagine it's a desktop sitting on someone's desk at their workplace. It'll be our client in this scenario, and we'll refer to it as computer 1. It's part of network A and has been assigned an IP address of 10.1.1.100. Now, let's put another computer on one of our other networks. This one is a server in a data center. It'll act as our server in this scenario, and we'll refer to it as computer 2. It's part of network C and has been assigned an IP address of 172.16.1.100 and has a web server listening on port 80. An end user sitting at computer 1 opens up a web browser and enters 172.16.1.100 into the address bar. Let's see what happens. The web browser running on computer 1 knows it's been ordered to retrieve a web page from 172.16.1.100. The web browser communicates with the local networking stack, which is the part of the operating system responsible for handling networking functions. The web browser explains that it's going to want to establish a TCP connection to 172.16.1.100 port 80. The networking stack will now examine its own subnet. It sees that it lives on the network 10.1.1.0/24, which means that the destination 172.16.1.100 is on another network. At this point, computer 1 knows that it will have to send any data to its gateway for routing to a remote network, and it's been configured with a gateway of 10.1.1.1. Next, computer 1 looks at its ARP table to determine what MAC address of 10.1.1.1 is, but it doesn't find any corresponding entry. Uh-oh. It's okay. Computer A crafts an ARP request for an IP address of 10.1.1.1, which it sends to the hardware broadcast address of all Fs. This ARP discovery request is sent to every node on the local network. When router A receives this ARP message, it sees that it's the computer currently assigned the IP address of 10.1.1.1. So it responds to computer 1 to let it know about its own MAC address of 001122334455. Computer 1 receives this response and now knows the hardware address of its gateway. This means that it's ready to start constructing the outbound packet. Computer 1 knows that it's being asked by the web browser to form an outbound TCP connection, which means it'll need an outbound TCP port. The operating system identifies the ephemeral port of 50,000 as being available and opens a socket connecting the web browser to this port. Since this is a TCP connection, the networking stack knows that before it can actually transmit any of the data the web browser wants it to, it'll need to establish a connection. The networking stack starts to build a TCP segment. It fills in all the appropriate fields in the header, including a source port of 50,000 and a destination port of 80. A sequence number is chosen and is used to fill in the sequence number field. Finally, the SYN flag is set and a checksum for the segment is calculated and written to the checksum field. Our newly constructed TCP segment is now passed along to the IP layer of the networking stack. This layer constructs an IP header. This header is filled in with the source IP, the destination IP, and a TTL of 64, which is a pretty standard value for this field. Next, the TCP segment is inserted as the data payload for the IP datagram, and a checksum is calculated for the whole thing. Now that the IP datagram has been constructed, computer 1 needs to get this to its gateway, which it now knows has a MAC address of 001122334455. So an Ethernet frame is constructed. All the relevant fields are filled in with the appropriate data, most notably the source and destination MAC addresses. Finally, the IP datagram is inserted as the data payload of the Ethernet frame, and another checksum is calculated. Now we have an entire Ethernet frame ready to be sent across the physical layer. The network interface connected to computer 1 sends this binary data as modulations of the voltage of an electrical current running across a Cat6 cable that's connected between it and a network switch. This switch receives the frame and inspects the destination MAC address. The switch knows which of its interfaces this MAC address is attached to and forwards the frame across only the cable connected to this interface. At the other end of this link is router A, which receives the frame and recognizes its own hardware address as the destination. Router A knows that this frame is intended for itself, so it now takes the entirety of the frame and calculates a checksum against it. Router A compares this checksum with the one in the Ethernet frame header and sees that they match, meaning all of the data has made it in one piece. Next, router A strips away the Ethernet frame, leaving it with just the IP datagram. Again, it performs a checksum calculation against the entire datagram, and again, it finds that it matches, meaning all the data is correct. It inspects the destination IP address and performs a lookup of this destination in its routing table. Router A sees that in order to get data to the 172.16.1.0/24 network, the quickest path is one hop away via router B, which has an IP of 192.168.1.1. Router A looks at all the data in the IP datagram, decrements the TTL by 1, calculates a new checksum reflecting the new TTL value, and makes a new IP datagram with this data. Router A knows that it needs to get this datagram to router B, which has an IP address of 192.168.1.1. It looks at its ARP table and sees that it has an entry for 192.168.1.1. Now, router A can begin to construct an Ethernet frame with the MAC address of its interface on network B as the source and the MAC address of router B's interface on network B as the destination. Once the values for all fields in this frame have been filled out, router A places the newly constructed IP datagram into the data payload field, calculates a checksum, and places this checksum into place, and sends the frame out to network B. Just like before, this frame makes it across network B and is received by router B. Router B performs all the same checks, removes the Ethernet frame encapsulation, and performs a checksum against the IP datagram. It then examines the destination IP address. Looking at its router table, router B sees that the destination address of computer 2, or 172.16.1.100, is on a locally connected network. So it decrements the TTL by 1 again, calculates a new checksum, and creates a new IP datagram. This new IP datagram is again encapsulated by a new Ethernet frame, this one with the source and destination MAC address of router B and computer 2. And the whole process is repeated one last time. The frame is sent out onto network C. A switch ensures it gets sent out of the interface that computer 2 is connected to. Computer 2 receives the frame, identifies its own MAC address as the destination, and knows that it's intended for itself. Computer 2 then strips away the Ethernet frame, leaving it with the IP datagram. It performs a CRC and recognizes that the data has been delivered intact. It then examines the destination IP address and recognizes that as its own. Next, computer 2 strips away the IP datagram, leaving it with just the TCP segment. Again, the checksum for this layer is examined and everything checks out. Next, computer 2 examines the destination port, which is 80. The networking stack on computer 2 checks to ensure that there's an open socket on port 80, which there is. It's in the listen state and held open by running Apache web server. Computer 2 then sees that this packet has the SYN flag set. So it examines the sequence number and stores that, since it'll need to put the sequence number in the acknowledgement field once it crafts the response. After all of that, all we've done is get a single TCP segment containing a SYN flag from one computer to a second one. Everything would have to happen all over again for computer 2 to send a SYN ACK response to computer 1. Then everything would have to happen all over again for computer 1 to send an ACK back to computer 2, and so on and so on. Looking at all of this end to end hopefully helps show how all the different layers of our networking model have to work together to get the job. I hope it also gives you some perspective in understanding how remarkable computer networking truly is. Even more remarkable than that, you for making it through this module. Now it's time to apply your new knowledge to the next.
Yeah. So I hope that gave a good picture of how all the layers are connected together. So the Ethernet frame that he was talking about was basically the data link layer, which is used here. So the Ethernet layer was data link layer, and then the IP layer was networking layer, and then the TCP layer was the transport layer. So all those were connected together and then sent to the data. Yeah. So again, if you have any questions, you can ask now. So you can ask anonymous questions through menu.com if you have any questions. Yeah, looks like no questions are there. So I guess we'll continue on with the next slide. So basically now I think we'll just go through some demos, and then after that we go through some more theory. And yeah, so you can do it along with me. So it's basically just a very introductory level to find IP addresses, how the data gets transferred, things like that. So yes, first we'll go through this. We'll first find your own private IP address. So what you need to do is you need to go to command prompt. You can write CMD in the search button, or you can go to Windows R and then press CMD. So yeah, if you can do it along with me, it would be good. So once you're there, you can find your private IP address by writing ipconfig. If you're using Linux, you can use ifconfig. So the private IP address, in my case, it is 192.168.1.7. So it'll be under Wi-Fi because I'm using Wi-Fi right now. So if you're using Ethernet cable, then it'll be under Ethernet. So yeah, I hope you are able to do that. Yeah, if you have any questions, you can interrupt me in between. So this is my private IP address. So 192.168.1.7 is my private IP address. So the next one, we'll try to find what is my public IP address. So for that, we'll just go to google.com and then you just write what is my IP. So it shows you a new IP. It is 117.215.197.22. So the previous one was 192.168.1.7. This is the private IP, which is my laptop's IP within my network. So this public IP address that you see is my public IP address, which is basically my router's IP address. That is generally the same for probably number of days, but depending upon my service provider, they may change the IP address as well. This IP address as well. Yeah, so that's how we get the public IP address. So you can do that, and then yeah, that's the next. We can try to find the Google's public IP address. So it's basically, I mean, you all do it. I hope. So we can just write ping google.com. The ping is basically just checking if the remote host is available or not. So that's one use of ping. So when I did ping google.com, I got the public IP address as 142.250.76.46. So can you guys do it and then just post it in the chat box so that we know what IP addresses we're getting. Yeah, so we're getting few IP addresses. So yeah, I'm not sure why you got IPv6. So this is the one that Priyanshi sent is an IPv6 address. The one that Praveen has sent is an IPv4 address. So the reason we have multiple IP addresses that we're getting. So the reason that it's not the same IP address for all of us, it's because Google has multiple data centers across the globe, and it is for redundancy. It has multiple servers across. So the same web page will be hosted across places. And when I'm trying to ping google.com, it tries to get the nearest server that is hosted nearby my place. So that is why I'm getting a different IP address from what Praveen and Priyanshi has got. Yeah, so that's about Google's address. And so now what we can do is we can access Google's public IP address from our web page. So I was talking about how to access the service on a device. So you can access the IP address along with its port address of 80. So you can see that you get the google.com itself. So similarly, I think you can use 443 with HTTPS, and then you get then it shows that it's not private, but yeah, you can get google.com. So google.com, that website is hosted on two different ports, 80 and 443. So 443 is a secure version which is using HTTPS. Yeah, so that is that's about Google's public IP address. And next, we can try to find the number of hops that are required to reach Google server. So that we can use a command called traceroute, TRACERT, google.com. So in Linux, it is traceroute, google.com, while in Windows, it is traceRT, google.com. Yeah, so it will take some time. So it goes through each device that the data is getting transferred to. So it initially goes to my router, which is 192.168.1.1. Then it goes to some other server, which is probably DNS server or something. Then it goes to one server on BSNL. So this one server, BSNL is one server. then it goes through multiple servers, multiple hops, and then finally it reaches Google's server. So if you wait for some more time, you'll get that information. Yeah. So yeah, while you're doing that, I think we can go to the next one. So yeah, so you can find the IP, you can find the DNS and the DHCP servers that you are connected to. So DNS server is basically the server that gives you the IP address for a particular domain name. If you give google.com, well, this server gives you what IP address you should be going to. So for that, you can just write ipconfig/or, ipconfig/or. And then you get all this data. So here you can see that the DNS servers are, I'm using 2 DNS servers. Similarly, the DHCP server is basically my router itself. The DHCP server is to give me an IP. So that server gives me an IP when I'm asking for a MAC address. When I'm giving my MAC address, the DHCP server gives me the IP address. So yeah, so this DNS server, I can actually check where this server is, what details about the server. So you can go to this website, whois.domaintools.com. I will post it in the chat. Yeah, Arpita. So it's it's basically the XXX is basically the first 3 octets of your IP address, and /64 will be. I think it's just I think a few hosts are there. So as I showed earlier, /24 means you have a large number of hosts in the network. So I'll go back to that once again. Yeah, so in this example, 192.168.0.0/24, it means that this network has this many hosts. So if your device is showing this number, then it means that you're in a network which is having this many hosts. Yeah, so in your case, it /64, I think it probably means maybe just around 10 hosts or something. So that many hosts will be there in your network. Yeah, so we'll go to this website. So this basically gives you information about the IP addresses that you are giving. So yeah, this is a DNS server. So I'm checking the DNS server, where this DNS server is, what it is, who is owning it, like that. So for me, it is going to the Indian Sansad Internet Backbone. So it's BSNL's DNS server. So you can find all the details about this particular server that is. Yeah, you can. Yeah, actually, if you go to some websites, you can even get the approximate geographical location of the IP address as well. So that's about DNS server. So this DNS server is one that is giving me what IP address google.com is or facebook.com is. So when I'm pinging google.com, this is the particular IP address. This is a particular DNS server which is giving me this data about which IP address google.com is. So yeah, so that's about DNS servers. Then next, what you can do is you can find the open ports in your device. So the open ports are basically the service. I was talking about the services that you're running in your device. So you can have websites and game servers. So your own device will be having many ports that are already open. So you can use netstat -ab in your CMD. So then it will say that it requires elevation. So you need administrator privileges to do this. So you can go to CMD, Windows CMD, You can press right click on this, and then you can click run as administrator. So now it's in administrator mode. So now you can write the same command again, netstat -ab. So then it gives all the IP, all the ports that are open. So yeah, so these are the ports that are open, and it 0.0.0.0 means that it is listening to other devices. Sorry. Yeah, you can see the services that this port is using as well. So like SVC host is using port 135 and port 445, and yeah, so yeah, like see the Chrome.exe is using for 49308 as the host, sorry, as a port. So what this means is my outgoing port is 49308. So Chrome.exe is using 49308, and let's say Google.com is using port 80 or port 443. So that is how Google's server is communicating with my device. So my device is using 49308 as the outgoing port. So yeah, in the same way, you can also use netstat -an to get a more detailed information. So some of these ports are using UDP instead of TCP. So you can get that information as well. Yeah. So as you can see, most of the numbers are very large numbers, like 49664, 49671, because these are outgoing ports. Because I'm not running a server in my device, like a web server and all. I'm not running. So if I'm running like that, it will be mostly small numbers. But since my since it's mostly outgoing ports, it's mostly large numbers. Yeah. So the final demo is we can find the network data transfer that is going on while you're going to google.com. So for this, you just have to go to your browser. If you're using Google Chrome, you can do Control-Shift-I or right-click and inspect. In other browsers also it will be similar. You can press right-click and inspect will be there. Then you can go to network. So this console will show you all the networking activity that is going on while you're accessing a website. So let's say you go to google.com. So you can see all the transfer is happening. So yeah. So when Google says it is only took 1 second or 2 seconds, you can actually verify it if it only took 1 second or 2 seconds. So yeah, to get the first document, first information from google.com, it took how much? 380 milliseconds. Then the full data, it sum up the full thing. So if you click on this, you'll get what all data. So this is what my computer sent. So it requested this URL. It used this method get, and then it got the code. Okay, you can the server gave me this. You can get the web page, and then the remote address is this. This is a server's IP address, and the port is 443. So when I get the data back, so these are the response headers, the packet headers, and then the request headers. This is the one that I sent to Google, and then Google sends me this data back. Yeah. So this is basically the cookies that I am sending like that. So yeah, you can get a very brief idea of what is going on when you're actually entering google.com. So this is what is going on in the background. So here it is getting an image like that. So if you go to some other web page, it probably get a lot more data than what you get here google.com. Yeah. So if you have any questions, you can ask me. I check that also. Yeah. So yeah, I'm running out of time, so I'll just go through this very briefly. So we'll go through some basic protocols. One is first is the application layer protocols. So the application layer protocols, you have the HTTP and the HTTPS. The HTTP is you have the web browsers which are hosting websites. HTTP is not that secure in terms of the encryption. So the data that is being sent, it's not secure in the encryption. The eavesdropper can get the data. So HTTP is secure HTTP, which even if the eavesdropper gets the data, it cannot get the original data back because it's encrypted. So it uses a client-server architecture. Then you have the DNS. The DNS it's used for name resolution. Like I ask for google.com, then the DNS server tells me this is the IP address for google.com. So basically what I did earlier. So we ping google.com, the DNS server tells me this is the IP address that is there for google.com. So similarly, you can find the DNS server for your own device using ipconfig/od. Then there's something called Telnet and SSH. Telnet and SSH, they are used for connecting to a remote host. So in Windows, there's something called a remote desktop. You can actually access another device remotely and access their desktop completely remotely. In the same way for Linux, you have SSH and Telnet. So you don't have a GUI, as in you can't see the desktop and all, but you can access the files. You can create files. You can remove files. You can execute files. Such kind of things you can do remotely. For that you get Telnet and SSH. So SSH is secure. Telnet is not secure. So in a similar thing, so there's something called a FTP. FTP is for file transfer. So the file transfer FTP server will be there. That is hosting some files, and then your computer wants to get that data from that server. So you ask for files from that, and then you get the data. So one of the software that is openly available for performing this is Filezilla. You can create your own FTP server in your desktop, and from another machine, you can access the files that is hosted on your server. Then you have SMTP, POP, and IMAP. These are mail servers, mail protocols. So SMTP is used for sending out mails. So your device, let's say you want to send mails out, so that uses port 25. It uses for 587 and 465 also. And then POP and IMAP, they're used for receiving the emails. So some small differences about deleting mails that are already received. That's one of the main difference between POP and IMAP. So it uses these ports. So I mean, if you go to gmail.com, I mean, you send the mail, probably what it happens is you actually use HTTPS instead of SMTP and POP and IMAP. Probably the Gmail's servers in the backend will be using SMTP to send the email, but from your end you'll be using HTTPS instead of SMTP. But I think if you're using Outlook, then Outlook will be using SMTP. And then the transport layer protocol. So the transport layer protocols are TCP and UDP. TCP is used for reliable connection for data transfer. So it checks if the data is actually received by the server or not. UDP it's unreliable. So if for TCP connection, it does a connection first, then sends the data. So it is a SYN. Then server says I accepted the SYN. Then you again accept the accepting of the SYN, and then you send the data like that. Then, but for UDP, the server asks you for some data, so it just keep sending data. You don't check if the data is actually received by the server or not. So TCP, I mean, you use it for file transfer so that you know that the file is actually received by whoever is asking. But UDP you can use, I mean, in this case, if you're using Google Meet, it mostly uses UDP because you don't need to receive all the data of all the frames. So even if some frames of video is lost, it is fine. So it just keeps sending the data, no matter it doesn't matter if all the data is received or not. So then there are network layer protocols. So network layer protocols, it's ICMP. It's mainly to find if there are any errors in the network on the devices. So the ping uses ICMP. So it gives echo request if the host is there or not. Then the echo reply, the host is there. Then some errors, destination is unreachable, router is overloaded, time is exceeded, like that. So those kind of errors in the network, you can find out using this ICMP protocol. Then data link layer protocols. So in this, we have the ARP. Yeah, so there's ARP, RARP, BootP, and DHCP. So ARP is mainly used for getting the MAC address from the IP address. So it basically checks, it gives an IP address, and then the node, it asks, I mean, the system may ask who has, I mean, what is the MAC address of this IP address, and then system B will respond, this is the MAC address for this particular IP address. So that protocol is called ARP. So I think in that video he was saying about ARP requests. So this is what is happening. So in RARP, the reverse form. So the host says this is my MAC address. I want an IP address. Then the RARP server says, see, this is the IP address. You can take it. So it may ask for itself also, that I want this MAC address for myself, and I want this IP address for myself. So it gives an IP address. So it can, for the RARP protocol, it can only be used for I mean, each network needs an RARP server. It can't be used, I mean, for one RARP server cannot be used for multiple networks. Each network needs an RARP server. So that is difficult. So that's why they set up for BootP. BootP, it can go across multiple networks. The same thing happens. So it asks for a MAC address. It gives the IP address. But it has something called static IP addressing. So it reserves IP addresses for these hosts. Even if the host is not using that IP address, even then it is statically assigned. So that's why they came up with DHCP. DHCP is dynamic IP addressing. So whenever a host asks for IP address, it gives an IP address. If there are any IP addresses that are not being used, it gives it to any new nodes in the network. So the IP addresses are not gone waste. That's why DHCP is being used. So in all the networks, it uses DHCP. So routers will have DHCP on it. So these two are application layer protocols, BootP and DHCP. Then the Ethernet also is a protocol which is in the data link layer and the physical layer. So it uses logical link control, medium access control. So it checks for if the medium is free or not, and it also checks for the flow control and all those things that I discussed earlier. So yeah, then we have some network algorithms. So one is for pathfinding. So it's about finding the shortest path between two nodes. There's an algorithm called Dijkstra's algorithm that is used for finding the shortest path between two nodes. And shortest path problem is there, which is used to find the path between two nodes, which has the sum of weights, which is minimized. So pathfinding is like this, which is the shortest path. And then shortest path is for finding the path which has the least weight, sum of weights. And then the spanning tree algorithm is to prevent switching loops. So when the network has broadcasting on it, it causes some issues because it keeps on broadcasting. So to prevent that, there's an algorithm called spanning tree algorithm. It prevents data from continuously being broadcasted in a loop. So, and then there is minimum spanning tree. So it's basically a subset of the edges which connects all the vertices, and there are no cycles in that particular edge. So if this is a graph, this is one spanning tree. There are no cycles in that. But the minimum spanning tree is the one that has the least cost. So this is actually 3 and 5. This is actually 1, 1, 3, and 2. So that is lesser. So that's a minimum spanning tree. So it's used for network device designs, and it's used to solve problems like the traveling salesman problem. And then the medium access control is there, which is CSMA CD and for Ethernet, and CSMA CA for wireless networks. So TDMA, FDMA, CDMA, which is time dimensional multiplexing, and frequency division and code division. So for medium access control in Ethernet, what happens is the device checks if there are the medium is free. If it sees it is free, it sends the data. But if there is a collision that occurs when the data is being sent, it senses that collision, and then it again sends the data. But the timer keeps changing so that the nodes send the data one after the other finally. So that's what happens in the CSMA CD in Ethernet. So yeah, so this is basically the algorithm. It waits for the carrier to be free, and then it sends the data. The timer keeps changing based upon an algorithm called backoff algorithm. Yeah, there are some algorithms called flow control to prevent the receiver from receiving more data than it should be. So there are 3 flow control methods. So one is stop and wait, go back, and salty repeat. So stop and wait is basically you send the data and you wait for an acknowledgement. If it doesn't receive an acknowledgement, it time out, and then you send the data again, and then you get the acknowledgement. Then go back and you keep sending data. If even if you don't wait for the acknowledgement, you keep sending data. But if you don't receive an acknowledgement for one data that is sent, it times out, and then you start from that particular data, and then you send all the other data again. So this is useful in reliable links. If you have unreliable links, you have selective repeat. You do the same thing again. You keep sending data, but if one data is lost, you time out, and then you send only that particular data. You don't send the full data again. So, but it's computationally more complex than go back end, but it's useful for unreliable links. You don't have to keep sending so much data. And then finally, some network security to end the day. So we have encryption. So it's you have private key encryption and public key encryption. Private key encryption is basically you have single password for both users, and both users use the same password to encrypt and decrypt. So one of the protocols is AES, which is very secure, and public key cryptography is there, which in this one encryption is being done by one public key, which is available to both parties. So which is available to both parties, but decryption is done by a private key, which is available only to one particular party, which is Bob in this case. So yeah, in the similar way, there's something called message integrity. You want to check if the message is tampered or not. So when the message is sent, you add an extra SHA-1 or MD5 message digest, which is based upon the data that you sent. And then when the receiver receives it, it checks if the SHA-1 or MD5 is correct based upon the data that you sent. Then it sees that the data is correct. It's like a checksum or CRC. Then key exchange. Key exchange for private key cryptography. So what happens is, in secret key, the private key encryption, you need to first make sure that this is the secret key that you want to use for all communication. So how do you send the secret key to both parties so that that this is what is being used? But because if you send the secret key, the attacker can get that secret key and then use it. So Diffie-Hellman algorithm is used for this very purpose. So this algorithm, it basically each party has a particular uses a particular data to encode that message, and then that data is being sent to both parties. And then when they use the same data to on that message that is received by the other party, then it gets another secret which is common to both. So this is basically the secret key that is used for encryption. Yeah, so that's basically it. Thank you. So if you guys have any questions, you can either ask or you can put in the chat box. Yeah, thank you guys. I think Praveen, you can continue if there are no more questions.
Hello everyone. Thank you for attending today's tutorial, and thank you, Mr. Varki, for the amazing presentation. So, if you have any questions about today's topics which are covered and anything, you can always post in Slack. I will share the resources for my part, and I request Mr. Varki to also share resources for his part. So the recordings, some of the attendees had requested about the recordings. So the recordings will be shared after the sessions, and for the lectures, we'll ask the permission of the professors and then share them. Tomorrow we'll have our first lecture at 10 a.m. And we'll proceed with the same link. So if anyone has any issues joining the lecture tomorrow or anything, just email me anytime and I'll invite you to the meeting. So apologies for any issues you had today. I hope everything goes on smooth tomorrow. So I hope everyone received the problem sets. Please do take a look. They cover topics from lecture 1, 2, and 3. So if you have any questions, you can always post in the Slack or also ask tomorrow in the tutorials. So I'll see everyone tomorrow. Thank you. You may leave now.